Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterman. So in this class, we'll try to completely characterize antenna. So what are the parameters which will characterize an antenna, differentiate or specify an antenna? So we'll see that there are two types of characteristics which are dependent on how you observe the antenna based on what concepts, field concepts or circuit concepts. So you know that antenna can lose free space wave in a desired direction. This directional characteristics of antenna can be observed from the radiation characteristics of the antenna. So for the radiation characteristics of the antenna, you need to know the field concepts of the antenna. Another thing is that antenna is connected to a transmission line. It can be assumed as a load to a transmission line, and we can find its equivalent circuit, and we can find out the input characteristics of the antenna. And input characteristics of antenna can be studied from the circuit concepts. So this diagram shows you the input characteristics of antenna and radiation characteristics of the antenna. So now antenna is connected to the transmission line at the end, so we can consider this as a load to the transmission line and study the input characteristics of the antenna using the circuit concepts. And once the field which was guided wave inside the transmission line is converted using antenna as a radiated fields, we'll look at the fields from the field concepts and we'll be able to study the radiation characteristics of the antenna. Some of the radiation characteristics of antenna are radiation pattern, directivity, gain, polarization. Input characteristics of antenna are input impedance, bandwidth, reflection coefficient, voltage standing wave ratio, BSWR. So in order to understand the radiation characteristics of the antenna, we need to know one parameter which is called radiation intensity. Using radiation intensity, we can define gain, directivity of the antenna. So in order to understand radiation intensity, we need to know what is solid angle of an antenna. Solid angle, we need to define what is solid angle. Solid angle is denoted by d omega here. The area subtended by this solid angle on the spherical surface will denote it dA. Radius of the sphere is r. So in that case, d omega is defined as dA by r square. It is the ratio of the area subtended by the solid angle to the square radius. So what is this dA here? So this is a direction which is normal to the surface element dA, and that is the direction of the surface element. So if direction of the surface element is along the radial direction, I can find out dA as s2 d theta, s3 d phi. What is s2 and s3 for the spherical coordinate system? R sine theta, so it becomes r square sine theta d theta d phi. D omega in that case will become simply sine theta d theta d phi. So how do you define radiation intensity? Radiation intensity is defined as power crossing per unit solid angle. What is power crossing? Power crossing can be found out from the Poynting vector. Poynting vector is power density. You multiply by area, you get the power crossing. So SdA will give you the power crossing. You divide it by the unit solid angle d omega, you get the radiation intensity, which is denoted by u theta comma phi, and we can define it as, see, basically d omega is dA by r square. dA cancels out, it's simply r square s theta phi. So the unit of Poynting vector is watt per steradian. If you want to find radiation intensity u, you simply multiply r square to the Poynting vector s. Let us take simple example for the Hertz dipole. For the Hertz dipole, you know the electric field, you know the magnetic field. You take cross product of these two, E cross IC star, you will be able to get the Poynting vector. So you multiply by r square, then you get the radiation intensity. So the final term you have here for the radiation intensity is independent of r square. We don't have any R dependent term here. And most of the time we are interested in the normalized radiation intensity, which is a dimensionless quantity. So normalized radiation intensity is defined as U divided by U max. U is the radiation intensity in particular direction theta phi. U max is the maximum radiation intensity. So maximum radiation intensity will be when theta is equal to pi by 2, then this term goes away. So the ratio of U max by U max will be simply sine square theta. And we usually plot radiation pattern in dV. So this is the power. So U normalized in dB will be 10 log 10 sine square theta. So you plot this with respect to theta, you get the power pattern of the antenna. You can also find out total radiated power from the antenna by integrating U with respect to d omega. What is the total solid angle of a sphere is 4 pi over the whole solid angle. If you radiation intensity, if you integrate it over the whole solid angle, you get the total radiated power. D omega is sine theta d theta d phi. So you integrate u theta phi. For phi going from 0 to 2 pi, theta going from 0 to pi, you get the total radiated power. There is one very useful term here which is called the average radiation intensity. So how do you define average radiation intensity? Is the total radiated power divided by the total solid angle, which is 4 pi. So that will be 1 by 4 pi of the total radiated power. So this is actually the radiation intensity of an isotropic antenna. What is a radiation pattern? It is a 3D graphical plot of the radiation fields of the antenna as a function of spherical coordinates theta and phi. You can also have power pattern, but if you want to have field pattern of the antenna, what you do is you imagine that antenna is placed at the origin of a spherical coordinate system, and you measure the electric field at the distance r for different values of theta and phi, and you plot it. That is your field pattern of the antenna. This is the typical radiation pattern of a dipole antenna. Dipole antenna with upper arm and lower arm. Total length is lambda by 2. Lambda by 2 dipole antenna is the most popular antenna, and it will have a radiation pattern like this. So now fields, you can look at the fields from two planes. One is E plane, another is H plane. So this is a 3D pattern. You can have two principal cut planes here, one in the XY plane, another in the XZ plane. When you cut this 3D radiation pattern in the XY plane and the XZ plane, you will have two patterns, one for the E plane, another for the H plane. So now if you assume current is flowing along the Z axis, so magnetic field circulates the current, so magnetic field will confine in the XY plane. So magnetic field will be confined in our case in the XY plane. So the plane in which we have the maximum electric field is called H plane. And you look at the XZ plane, electric field will be confined in this plane. So the plane in which you have maximum electric field is called the E plane. So if you look at this pattern in the XY plane, it's always a circle. There is no variation of field with respect to phi. But if you look at the field in the XZ plane, you have maximum radiation when theta is equal to pi by 2, minimum radiation when theta is equal to 0. It looks like a H shape. So you have a directional pattern in the E plane and non-directional pattern in the H plane. Such kind of radiation patterns are called omnidirectional radiational pattern. Isotropic antennas are not existing in the nature, so if you want to have proper radiation from all directions, we use omnidirectional antenna like this. You can also have a directional antenna. If you want to confine power in one direction, you need to use directional radiation pattern of the antenna. This is a horn antenna. This is the waveguide which is feeding this horn antenna. So if you just keep your waveguide open here, the impedance of the waveguide and that of the free space doesn't match. So in order to do proper impedance matching, we flare out the waveguide at this point. the impedance of this horn antenna actually matches with that of the free space impedance, which is 377 ohm. So signal which comes from the waveguide would be able to radiate properly in the free space because of the proper impedance matching. So this is the radiation pattern of a horn antenna. It has a highly directive pattern and gain is very high. Typical gain is around 18 dB. So there are two types of plane. One is field pattern, another is power pattern. In the field pattern, you plot normalized electric field or magnetic field with respect to theta and phi. Once you fix R, the field dependence with respect to R can be neglected. Or you can also plot power pattern, which is basically normalized radiation intensity versus theta and phi. As you know that 3D pattern is very difficult to draw on a 2D plane, so we usually have two principal cut planes, E plane and H plane. We have already discussed that. For the dipole antenna, XY is the H plane and E plane is the XZ plane. And this is a H plane pattern of the dipole antenna. What you can see is that in the XY plane, phi is varying from 0 to 360 degree. When you verify, the fields are not changing, so at any location fields is always fixed. So you have a non-directional pattern in the XY plane and you have a directional pattern here. You can see that in the XZ plane, in the E plane, when you vary theta, for theta is equal to 0, you don't have any radiation. When theta is equal to pi by 2, you have maximum radiation. So you have a directional pattern in the E plane, non-directional pattern in the H plane. This is omnidirectional radiation pattern. Besides this polar plots, we also have rectangular plots of the radiation pattern of the antenna. This is a typical rectangular plot of radiation pattern of the antenna. Here y-axis is the radiated power. We usually plot normalized radiated power in dB. So in that case, maximum dB will be 0 dB. And in this typical pattern you have here for the antenna, you have a lobe with the maximum radiation. This is called the main beam. You have other lobes with very less radiation. These are called side lobes. So maximum radiation is in the main beam. How much dB down from the main beam is the side lobe level is given by side lobe level. So here we have shown side lobe level is minus 15 dB. Lesser and lesser is better, because you will see that later on signals which has gone in the side lobe is actually wastage of energy and power. Here you have maximum radiation along this direction. This is called theta max, and you can see that the pattern is reaching 0 at this point, at this point, at this point, and at this point. These are called the nulls of the antenna radiation pattern, and the first two nulls are this. Angle between these two first null is called beam width between first null, BWFN, beam width between first two nulls. You also have, see, maximum is 0 dB, this is minus 3 dB point, this is minus 3 dB point. This angle is called the half power beam width. So now if you have a larger and larger value of half power beam width, you will have a broader and broader beam. And if you have a lesser value of half power beam width, you will have a narrower beam. So these parameters will specify the properties of the antenna radiation pattern. We have discussed all these things. So now why I am saying that side lobe level should be low, the signal which has gone in the side lobes is actually wastage of power. That is because you consider the case of microwave tower 1 and 2 fitted with transmitting antenna and receiving antenna. This is a main beam pattern of the transmitting antenna and receiving antenna. They are doing line of sight communication, and if we have some side lobes here, signal which has gone in the side lobes won't be able to reach this receiving antenna. So basically that's why it's a wastage of power. We also have back lobe. So now signal which has gone in back lobe is also wastage of power. We need to have minimum value of back lobe, and we should have maximum value of front lobe, which is the main beam. The ratio of these two is called front to back ratio, and we need to have higher and higher value of front to back ratio. So for example, for the horn antenna, this is the front lobe. this is the back lobe. The ratio of these two should be larger and larger. But the fundamental question is, at what distance from the antenna we are in the far field of the antenna. And nowadays we have many applications for the far field of the antenna, like mobile communication, wireless communication usually happens in the far field of the antenna. We also have applications for near field also. For example, wireless battery charging, wireless power transfer in the near field. We can also do wireless power transfer in the far field. All these things can happen either in near field or far field. We need to know clearly what is near field and far field distance. So now let's consider an antenna which is positioned at the origin. The maximum dimension of the antenna is Dmax. In that case, reactive near field region would be up to a distance of 0.6 to square root of Dmax cubed by lambda. As soon as you move out of this distance, you are in the radiating near field Fresnel region, and this will be up to 2D max square by lambda. Once you move out of this distance, you are in the far field Fraunhofer region. This is for distance which is greater than 2D max square by lambda. So how do we get this expression for the far field 2D max square by lambda? That is because, let us take this simple example. You have a source which is radiating spherical wavefront, but in the far field of the antenna you assume that this spherical wavefront is a plane wavefront. When we do that, how much is the error in the phase? What is the acceptable value of error in the phase when we assume that spherical wavefront has been converted into plane wavefront? And it was decided during the Second World War. What is the acceptable error? Acceptable error was, phase error was pi by 8. See, basically Dmax here is the maximum dimension of this antenna under this AUT. This is the Dmax. So this antenna is capturing this source wavefront. When it captures this source wavefront, how much error is there at the edges? Maximum error, permissible error. It was decided during the Second World War. It was pi by 8 because the accuracy with which phase can be measured during that time was pi by 8. So this phase error should be pi by 8. It should be lesser than that. Then we are in the far field of the antenna. So you have two kind of length. One is electrical length, another is physical length. Electrical length is defined as beta L. Beta is 2 pi by lambda. So here phase error is basically electrical length pi by 8. But what is the physical length? Physical length would be lambda by 16. So this phase error of pi by 8 basically means this distance between this, then this, between the plane wavefront and the spherical wavefront, which is captured by the AUT, would be lambda by 16. It has been given an exercise in the book I have written on electromagnetic field theory. If you want, you can explore. So how do you define directivity? So directivity is simply defined as radiation intensity in one particular direction divided by the average radiation intensity. What was average radiation intensity? It was total radiated power divided by the total solid angle, which is 4 pi. And I have also mentioned that average radiation intensity is the radiation intensity of an isotropic antenna. That's why when we define directivity and gain of the antenna, the reference antenna is isotropic antenna. It's the ratio of the radiation intensity of that particular antenna in that particular direction divided by the radiation intensity of an isotropic antenna. So you know that there is maximum radiation along theta max. So if you find out directivity along that direction, you have D max. If you find out directivity for theta null, you have D min, minimum value of the directivity, maximum value of the directivity along theta max. So D max is defined as U max by U average. So 4 pi U max divided by total radiated power. If you taken out 4 pi common, what you have is 4 pi by beam solid angle. What is beam solid angle? Beam solid angle is defined as the solid angle through which all the antenna power would flow if the radiation intensity was U max for all angles in beam solid angle. So in other words, if you assume that For all angles in beam solid angle, the antenna is radiating U max, then total radiated power in that case will go through the beam solid angle. And this beam solid angle can be found out easily when you have a narrow major beam and negligible side lobes. In that case, you just find out half power beamwidth in theta in radian and half power beamwidth in phi in the radian. Then you multiply those two, you will get the beam solid angle. So Dmax is defined as 4 pi by beam solid angle. Beam solid angle you can replace using this formula. And you can even convert this theta half power beamwidth in degrees and phi half power beamwidth in degrees. The expression you have for Dmax is 41,253 half power beamwidth in degree in theta and half power beamwidth in degree in phi. So now when we define directivity, we have not considered losses into account. We have neglected it. But antenna is usually made up of metal conductors or dielectrics, so all these conductors and dielectrics have some inherent losses. So the definition is not proper. We need to consider losses also into account. That is taken care of by defining another antenna parameter which is called gain of the antenna. So when we define gain of the antenna, we actually define gain as 4 pi u theta phi divided by power input. What was the definition of the directivity of antenna? It was d theta phi is equal to 4 pi u theta phi divided by power radiated. So the only difference you have here is in the denominator. In the case of directivity, this is power radiated, but here we have power input. So why we are defining it like that? It's because let's say the input to the power is P input to the antenna is P input, total radiated power is P radiated, efficiency of the antenna is P radiated divided with power input. In that case, we have taken the losses into account. And radiation efficiency always less than 100% because there is always some losses in the antenna. It can be dielectric loss or conductor loss. So now in that case, I can replace power input by power radiation divided by efficiency of the antenna. So look at this term here. These terms look like directivity of the antenna. So finally what you observe is gain of the antenna is efficiency into directivity of the antenna. So now here also when I define gain of the antenna, I am using 4 pi by power radiated. That is basically power radiated by 4 pi. Total power radiated by 4 pi is the average radiation intensity. That is the radiation intensity of an isotropic antenna. So when we define gain, isotropic antenna is used as a reference antenna. So that's why we always measure gain in terms of dBi. dB over isotropic. Isotropic antenna is the reference antenna for the gain measurement. Yes, you know that antenna is a passive device. It will not amplify any power. Then the fundamental question is, why do we have gain? Gain over what? That's the question I usually ask the students. So here the gain is with respect to the isotropic antenna. Is that okay? So when you have an amplifier, the gain is with respect to the input and output. Output should be always greater than that of the input power. That is the gain of the amplifier. But here it's not like that. The gain is with respect to the isotropic antenna. So that's why we measure gain as dBi, dB over isotropic. Let's discuss the Friis transmission formula. This is the first wireless experiment you can do. If you are interested in wireless communication, the first thing you can do is the experiment we are going to discuss now. Let's say you have a transmitter, you have a receiver. The transmitter is fitted with a transmitting antenna and receiver is fitted with a receiving antenna, and wireless communication cannot happen without antenna, so we need a transmitting antenna and receiving antenna. Assume that these two antennas are in the far field region. Distance between them is r, and we are transmitting some signals from the transmitting antenna, and receiving antenna is receiving that signal. The wavelength of the signal is lambda. The power transmitted from the transmitting antenna is denoted by Pt. Power gain of the transmitting antenna is Gt. Gain of the receiving antenna is Gr. we are interested in finding PR, is the power received by the receiving antenna. You can connect to a power meter and find out how much is the received power. So now this is actually mathematically given by Friis transmission formula, famous Friis transmission formula. If you want to find power received is simply PTGTGR lambda by 4 pi r whole square. That means when you increase the power which has been transmitted from the transmitting antenna, power received will be higher. If the gain of transmitting antenna and gain of receiving antenna is higher, you will have more received power. If wavelength is higher and higher, you will have more received power, but if wavelength is higher and higher, frequency becomes smaller and smaller. That means when you go for higher and higher frequency, wavelength will become smaller and smaller. So for higher frequency, power received will be lesser. If you go further away from the antenna, power will be also reduced as 1 by r square. So this is the famous Friis transmission formula. Why we are discussing it? We are discussing it because we want to define gain of the antenna. We want to measure gain of the antenna. we want to measure gain of the antenna using the Friis transmission formula. This is called gain transfer method. There are many techniques for finding gain. This is one of the popular method for finding the gain of the antenna. So assumptions made where antennas are placed in the far field regions. There is line of sight propagation between the two antennas. There is no obstruction in between, and we don't have any other sources interfering with the wireless experiment we have described before. And we also assume that there is no multipaths due to reflection, refraction, and diffraction. So how do I measure the gain now using the Friis transmission formula? So now I know how much is the power transmitted. I know what is the distance. I know the wavelength of the signal I am using. I know what is the power received. I can measure it. I also use an antenna with a known gain at the transmitter. GT is known to us. Then GR can be found out. GR is the only unknown in that case. You can find out like that, or you can use two identical antennas at the transmitter and receiver. In that case, GT and GR becomes equal. We call it G, and we measure G always in dB. So you can find G as half 20 log 10 4 pi r by lambda plus 10 log 10 PR by PT. So this is how you find out the gain of the antenna using gain transfer method. Let us quickly summarize what we have learned in this class. First thing is that we have seen that antenna characteristics can be broadly divided into two types. One is input characteristics, another is radiation characteristics. Input characteristics can be studied using the circuit concepts, and radiation characteristics can be studied using the field concepts. So for the radiation characteristics of antenna, the most fundamental parameter is the radiation intensity. Radiation intensity can be found out from the Poynting vector by simply multiplying with r square. And directivity of the antenna is basically ratio of the radiation intensity in one particular direction divided by the radiation intensity of an isotropic antenna. And when you multiply directivity with the efficiency, you get the gain of the antenna. Gain of the antenna is always measured in dBi, dB over isotropic. So the reference antenna is isotropic antenna. We are having gain with respect to that of the isotropic antenna. In the radiation pattern, we have defined many parameters. First thing is that radiation pattern is a 3D pattern plot of the power radiated or field radiated from the antenna for different values of theta and phi. But it's very difficult to have 3D radiation pattern plot on a 2D plane, so we have two principal cuts where you have maximum electric field and magnetic field, which are called E plane and H plane. E plane and H plane for a dipole oriented along the Z axis was XZ plane is E plane and XY plane is the H plane. And we have seen that antenna can have omnidirectional pattern, it can also have directional patterns. And we have also defined what are the main lobes, side lobes, how much is the side lobe level. Lower side lobe level is better for us. Lower front to back ratio of the antenna is better for us. We have also defined what is theta max, direction of maximum radiation. And we have also defined half power beam width. Broader the beam width for the main beam will have a larger value of half power beam width. We have also defined beam width between first two nulls. So all the radiation characteristics of the antenna has been defined in this class. We'll discuss about the polarization in the next class and along with the input characteristics of the antenna. Thanks for your attention.